Okay, Ji, let's formally get started for today. We are into week number 12, right? So, which means that we have around 4 weeks after this one. So, from the viewpoint of contents, we are pretty much on track. We're not lagging behind, or neither we are advanced too much. So since we are meeting after a break, so I'll just give you a recap and I will repeat the previous topic because I understand it was not very easy. So I'll give you a quick recap of what we were looking at, and then I will repeat this topic because it was the last topic in the last days of the month of Ramzan. So I understand it's not the ideal time to see this topic, which itself is quite challenging, right? So don't worry, I'll be repeating this. So just to remind you that after the midterm, we shifted to recurrent neural networks, right, which are basically designed to process sequential data. And we had seen some preliminary example that how you can do, for example, sentiment classification using recurrent neural network, right? So the general idea of recurrent neural network was that you have sequential data, means you have time. Okay, so it means that if I have a sentence, right, for example, if I have this sentence, repeating module in, so this is my first word, so you can say this is T0, then you have T1, T2, and so on. So you feed your data word by word, if we are talking about text, okay, to your model, and depending upon how many words are there in my sentence, I will unfold my network that many times, right? So it means that you have this repeating unit. What is going on in this unit, I'll just explain. So if you have 3 words, you repeat it 3 times. If you have 5 words, you just repeat it 5 times. Okay, and all the parameters which are in one box, they are same irrespective of how many times you repeat it. Okay, so you see it's quite powerful because otherwise, once we are dealing with text or something similar or speech or anything which is sequential, we cannot guarantee that what would be the length of the sequence, right? So with recurrent neural networks, we have this possibility that we feed it one by one different entities, which can be words or characters or whatever we are dealing with, and our parameters for each of these unfolded boxes remain the same. Now let's see what was going on inside the box. Okay, so you have this xt, which is the current input, right? So this is your input. For example, this could be a word. Okay, and what is coming from here, this is hidden state from the previous time step, right? So we said that it has some sort of memory. It is looking at the current input, which is xt, and it is also looking at the hidden state of t minus 1, which was basically the previous time step, right? So this is actually xt and this is actually ht minus 1. So actually what happens is that you have two weight matrices. Okay, one weight matrix, for example, wx, you multiply it with xt, and the second weight matrix is say wh, you multiply it with ht minus 1, and then you add vice, okay, vice vector depending upon how many neurons you have in this hidden layer, and then you apply 10h and it gives you the next hidden state. But we also said that instead of every time writing this, we have a compact representation that we combine the two weight matrices into a big matrix, let's call it w, and we also concatenate ht minus 1 and xt. It is just a representation so that I don't have to write it again and again. Okay, we can just concatenate the two weight matrices. We can concatenate the x and ht minus 1 so that our expression becomes simple. Okay, this is only for that purpose, nothing else. So what was happening in RNN was that we were doing this as many times as we like. And normally I keep telling you that in recurrent nets, you see, we have not made an output layer. So why is that so? Because it depends what problem you are solving. If you are solving a sentiment classification problem where you have seen the complete sentence and then you can have your output. Okay, you can have another weight matrix here and softmax layer, for example, if you are solving what is the rating of this review from 1 to 10. So you will have 10 neurons here and you can apply the softmax. But if you are solving a different problem, for example, named entity recognition, then you will have one output at every time step, right? Because we want to say, okay, this is name of a person, this is name of a person, this is not, this is not, this is not. Okay, so that's why since RNNs can solve different problems, it is normal that we do not show output. We just show the hidden state and depending upon the problem we are solving, we can connect the output layer where it is required. So this was the general concept of RNN, but we discussed last time that if your sequence is very long and you are trying to back propagate, you can say error to learn your weights, the problem is that RNNs cannot deal with very long sequences, right? Because we discussed in detail that when your gradient, you apply chain rule, gradient is multiplied again and again. So if your value is between say 0 and 1, you keep multiplying them, it will become smaller and smaller and smaller, right? So that's why the network finds it difficult to learn, and we call that the weights have saturated, means they are not changing. So for those problems, we introduce something which is called LSTM. Okay, so LSTM we had introduced last time, but I'll be repeating it today so that you can link it with the rest of the discussion. So if you remember, before we started our discussion on LSTM, I had given you some insights on what is a gate. Okay, so if you remember, I think I had given you example of a tap. Okay, I tried to draw it. Okay, so we had seen this example. I'm just repeating it, that if you have a tap, okay, and you have some water coming here, okay, if you don't want anything here, you will close the tap. Okay, if you open it fully, then whatever is coming from here, it will pass through. And if you open it maybe partially, like half of it, then maybe 50% of the water will flow. Okay, so this is the general concept of a tap that we use in our daily life. Now, the same concept we can use in this LSTM, which is called a gate. Okay, so gate is actually something which is regulating the flow of information. And how do we implement gate? We implement gate by a point-wise multiplication. Okay, so you have some information coming from here. Say I have information 8, 4, 6. This is my information vector of size 3. Okay, and what will pass through, I need to decide. Okay, so you see, since we are performing pointwise multiplication, if I multiply this vector by a vector of all ones, pointwise means first element with first element, second with second, third with third. Okay, so what do I get here? I get the same thing here. So it means the tab is fully open. Okay, similarly, if I don't want any information to pass, what I will do, I can simply have multiplied by a vector of all zeros. So when you multiply 846 by 000, what you get? Nothing. So it is like the tap is fully closed. And you can also say, okay, I want the tab to be, I want 50% of the information to flow. So what you can do, you can have 0.5, 0.5, 0.5. Okay, so everything would be half. You will be getting 4, 2, 3. And you can have different numbers at every position. You want this 8 to pass fully. You want this 4 to stop completely, and you want to block 4, and you want to allow 50% of this information to pass through. So you can have a vector like this. Okay, coming from here. Sorry, it is coming from here, not here. It is here actually. Okay, when you multiply them together, you get 4, 0, 3. Okay, so this is the information that you are letting through. Now, in order to implement it, it's fairly simple. We need to produce a vector which has values in the range 0 to 1. Okay, and we already know that we have a very useful function which is called sigmoid, which produces values between 0 to 1. So what we'll do is that here we'll have a sigmoid layer. Okay, so now you see this sigmoid will generate uh, a vector of size 3 ABC, and depending upon what information you want to let go, so what will happen is that this will be multiplied with ABC, and then as an output you can control or you can regulate the flow of information, right? So this was the general concept of a gate. Now keep this concept in mind, and then we move to the next discussion. This gate will be used when we are discussing LSTM. Okay, there will be 3 different gates that I'll introduce. So in simple words, if someone asks you in some interview, what is a gate, how a gate is implemented? So a gate is implemented by a sigmoid function followed by point-wise multiplication. Okay, please remember this point-wise is very important, right? Because if you do vector, matrix multiplication, there is some other process. Okay, point-wise mean you simply multiply the corresponding values together. Okay, and this also reminds me that in some cases when you are doing convolution in your midterm attempt. So that is also, you can say, you multiply corresponding elements together. Okay, you don't do matrix multiplication of a filter with an image. If you do that, you will be getting something else, right? That is not matrix multiplication. That is corresponding elements multiplied together. Okay. So now with this, you can say background, let's try to, you can say, see inside an LSTM. Okay, so I'll be repeating the previous discussion again. So let me just draw. Okay, maybe I move it slightly. Okay, let me just draw it again. Somewhere here maybe. Let's draw it here. Okay, so just like RNN, now this would be our LSTM cell, but what will be happening in it would be, you can say, more complex. Okay, so we start our discussion with drawing this. Okay, now, so this is an LSTM cell. Okay, and there are many things which are going on inside. So let's see what is going on inside. Okay, so this straight line which I have drawn, this is called cell state. Okay, cell state, just like hidden state, we are calling it cell state. Okay, since on the horizontal axis we have time, so you are feeding it with CT minus 1, and there is something going on inside, and then you get CT as an output. Okay, now what is going on inside? There are two operations. Okay, one is point-wise multiplication. Okay, and the other is that you will be adding something, which is point-wise addition. Now, what are those? We'll come back to that later. Okay, so let's say this is like a conveyor belt where you have information flowing into the cell and out of the cell, and in between you have two interactions. One interaction is point-wise multiplication, the other interaction is point-wise addition. Okay, now with that we just leave it there. We start some other discussion. We'll come back to it. Okay. Now we'll be making some gates inside the LSTM, and the first gate that we'll see is called a forget gate. Okay, so now let me tell you what is a forget gate, but before that we should know that what is coming inside. So from here you have ht minus 1, just like an RNN. Okay, and similarly here you have xt, just like an RNN, which is coming from here. Okay, so you see this part is same as RNN. The new part that you see is actually the cell state. Okay, now the first gate that we'll make here is called a forget gate. Now, what is a forget gate? I tell you in a while, but you know, for a gate, what we do? We simply put sigmoid, and it is followed by point-wise multiplication. And this we are calling forget gate, so I am denoting it by F. F is for forget. Okay. First, let me write its equation, and then we'll discuss why we need to forget something. Okay, because normally we want to remember things. Why we are saying that we'll be forgetting something. Ft, what is Ft? Ft is sigmoid applied to what? You have ht minus 1 xt coming here, just like an RNN, same thing. They are multiplied by a weight matrix, you add bias. Nothing new, exactly the same thing which is happening in RNN, except that we are using a sigmoid function. So WF, this is a weight matrix in which you have weight matrix for H as well as X concatenated. And here you have H T minus 1 and XT, means both are multiplied by weight matrices. Don't worry about the sizes. I will explain you in detail that how to compute the sizes of these matrices and so on. Okay. And then you add bias. So I call it B as subscript F for forget. And that's it. Now, why do we need a forget gate? Okay, so I think we discussed last time that when we are dealing with LSTM, and suppose we are dealing with textual data, okay, so you have a model, a language model, which is trained on maybe English text from many novels, right? So if you have some sentence like that, for example, Ali was going to play tennis, and then you say he also invited his friends and so on, right? So you see, LSTM is helping you predict the pronoun, that since Ali is the name of a male individual, so the pronoun would be he, right? Now, suppose after that you say, okay, some other you can say subject appears, which is a female, right? You say Sarah was also going to play tennis with her friend. And now the new subject is a female, so the pronouns must be she. Okay. So we need our model to forget Ali. We need our model to forget the information that the subject was a male. That's why we say forgetting information may be required, right? So if you are wondering why we need to forget something, so this is an example which actually explains that there can be a situation where we need to forget information, and what we forget is controlled by this forget gate. Okay, now let's make this further. Let's add further functionality to this. Now the next we'll be looking at two layers: candidate layer and input layer. Okay, okay. Let me rather change the color so that you can correlate the equation with the color. Okay, so maybe here we draw something in a different color. So it's the same thing which is coming here, means xt and ht minus 1. Okay, nothing new. So here we have 10h. Okay, and what it will produce, it will actually produce a candidate cell state. Candidate means this is the new information we want to add to the cell state. That's why we are calling it candidate. Okay, and how it is produced, it is again very simple. Ct is 10h, and rest everything stays the same. Only with w, instead of using, since w would be different for this, so instead of calling it wf, I'm using the subscripts c. ht minus 1 xt plus bc. Okay, so this is producing using the current input and the previous hidden state with some weight matrices. It is generating a candidate, means some new information which is added to the cell state. But what is added to the cell state is actually regulated by a gate, another gate, which is called input gate. Okay, so input gate will make a gate here, and you know that whenever there is a gate, you have sigmoid. Okay, so you see the same information is going to all of these. Now I'll explain in a while what is going on here. So this is our input gate, what you see in the orange. Very similar to FT, but the only difference is it will have a different weight matrix, right? So you see, IT is basically a vector, and you take point-wise multiplication with CT. So this IT is controlling which part of CT should go forward. Okay, so IT is actually regulating that what part of the candidate cell state must be added to the cell state, because now I'll connect these two. Okay, so first let me write the equation for IT. Again, all of these equations, if you see, they are exactly the same. For gate, we have sigmoid. For other operations, we have tanh. And all of the equations are, you have a weight matrix, and you multiply them by the hidden state and the current input, and you have a bias. Okay, so now you have both of these, right? So now is the time to update the cell state. Okay, and how do we do that? Now you see what is the new cell state, CT. Maybe I use the same color so that you can correlate. Yeah, so CT is actually, which is the new cell state. Now you see FT into CT minus 1 means you are forgetting something. So you write, this is coming from previous, and what you want to forget, that is controlled by FT. Now plus, what are you adding? This candidate controlled by IT. So you write candidate cell state controlled by the input layer. So now you see, if you just look at it, the red part, there are two operations. You are forgetting something and you are adding some new information. What you forget is controlled by the forget gate. What you add is controlled by the input gate. Okay, so you can actually correlate it with the diagram. Okay, now we are left with one final thing, that is we need to produce HT, right? Because that HT will be fed to the next time step as the previous hidden state, right? So for that, what we do, let me just draw it. Okay, so for that we have a gate which is called output gate. Okay. So again, for a gate, and what we do here is we take CT, we apply 10H on it, and then the output gate controls that what you will give output as HT. Now let me write it and then I explain. So HT is actually, okay, rather first let me write OT and then I write for HT, okay? Because HT will be computed from OT. So OT means the output layer or the output gate is sigmoid WO, exactly the same as others, HT minus 1 XT, and it will have, of course, some bias BO. So this is coming on this path, OT. Okay. And what is coming from here? From the top? From the top, you have 10H on CT, right? And then you take the, you can say, sorry, element-wise multiplication with OT, which actually gives you HT. Okay, let me just correct it. It's so that you use the same notation. It is element-wise product, and this is OT. Now you see this HT is basically a filtered version of CT controlled or regulated by the output gate. Okay, so you see there are plenty of expressions, but the key expressions are that you have three gates for get, input, and output. Then you have a 10H layer, which is generating the candidate cell state. And then you also have a, you can say, hidden state or the new hidden state for the current timestamp, which is regulated by the output. Okay. Now, maybe before the next step would be that I will show you some numbers that, for example, if I say the hidden state has two neurons, right? Two neurons means here I have two neurons. So it means the value that is here, it is a vector of 2. Okay, so how, similarly, this xt is a vector of size, say 3. You have a vector of 3. So what would be the sizes of these different matrices? Okay, and how you will compute the output size and how you will compute the number of parameters, right? But before that, the discussion till here, I can give you a quick review from the slides. So there is no new information. I'll just go to the slides and flash the same information which we have already seen, but we'll do it, you can say, in a formal way. Okay. So this is basically the, you can say, whatever is going on inside an LSTM cell, which we saw stepwise. So let me just revisit it, that this straight line which you see at the top of the cell, this is called cell state. Okay, and there are two interactions in the cell state. One is point-wise multiplication, the other is point-wise addition. What are those information? We wait for a while. Then prior to that, we discuss what are gates. So gate is basically implemented using a sigmoid activation function, because it gives you a number between 0 and 1, followed by point-wise multiplication. So you have some information coming from here, and this is actually regulating that what will go out. Okay, so it can totally block the information, it can let the information pass as it is, or it can partially let the information flow, right? So this is just a recap of, you can say, activation function, that you have the sigmoid, which gives you a number between 0 and 1, which can act as a gate. And this is showing you the point-wise multiplication, that you have some signal and this is coming from sigmoid. So you can actually control that, okay, this will pass 50% and this will be blocked, right? It's the same example which we discussed. And just for completeness, you also have that what is this plus? This plus is point-wise addition, in which you add corresponding elements. So you can add two vectors of size 3 corresponding elements together and you get a vector of 3, right? It is trivial, but just for completeness, it is present here. Okay. So this is where we started our discussion, that you have a forget gate. So you have information ht minus 1 and xt. You concatenate them. Okay. You multiply them via weight matrix, you add bias, and then you apply sigmoid. So you get this FT. The next thing, basically you have two things. One is the input gate, the other is the candidate layer. So for input gate, exactly the same equation as previous. The only difference is that we are using subscript I rather than F, because we are talking about input gate. And this CT is the candidate vector. which is basically again dependent on ht minus 1 xt, but a different weight matrix. And you have this bias vector, and you apply 10h, and later you will be updating the cell state. Now, this is the important part where we are updating the cell state. So you have information coming from here. ft, these both are multiplied. So this is that part. Okay, means you are forgetting something. And then here, what you are doing, you are adding something. What are you adding? It into this ct. So it into ct is added. Okay, so if you just draw this diagram stepwise, if you see it all of a sudden, these 5-6 equations, it may look a bit challenging, but if you go stepwise, it's fairly simple. And finally, we have the output layer, output gate, again sigmoid, some weight matrix depending on this, add bias. Okay, and then what is the ht? ht is coming from this path 10h and controlled by the output gate. Okay, so maybe this gives you a complete summary of you can say all these equations. There are like 1 2 3 4 5 6 key equations, but more or less the gates have exactly the same equation. Then updating cell state is you can see and update, and finally you have ht, which is controlled by output gate. Now, before moving further, it's a good idea that we discuss. Okay, now these equations look fine, but to develop further understanding, we take an example that okay, x is a 10-dimensional vector, means you have 10 values here. Okay, and this hidden layer has 2 neurons. Okay, means this purple cell, it has actually 2 neurons like this. Okay, so this purple cell is like this. So it means whatever is on this arrow, it is a vector of 2. Okay, similarly, whatever is the size of this, the same would be size of this. So this also means it would be a vector of 2 as well. Okay, of course there will be some different values, but now let's do some discussion that how we can compute the parameters, or how we can see the sizes of the vectors which are flowing on these different paths. Okay, so unfortunately I'll have to get rid of this illustration. Okay, so let's do it with only one gate. Okay, and then we can replicate. Let's do it only for the forget gate. So the expression for forget gate was sigmoid wf ht minus 1 xt plus vf. Okay, so if you remember, this, as I told you, is a compact representation. If I expand it, okay, so actually what is going on, this w, these are actually two matrices. One matrix is, I can call it maybe whf, which is multiplied with ht minus 1. And then there's another matrix, let's call it wxf, which is multiplied by xt. And then you have the bias vector. Okay, so both of these are actually same. Just one is the compact representation of the other expanded form. Okay, so this is also ft. Okay, now we are saying that my x is actually 10-dimensional. Okay, so this is my x, which has 10 values, means these are 10 neurons. Okay, and then your hidden layer has, say, let's assume 5 neurons. 1 2 3 4 5. Okay, so we just draw it like this, ht minus 1, but ht minus 1 is actually these 5 values. This is ht minus 1. Okay, so it is coming from here and it is coming from here. Okay, now you see actually all of these 10, they are connected to these 5, right? If you remember, we had this x and this is h, so you have 10 here and 5 here, so you have how many connections? 50 connections, right? Because all these 10 are connected to these 5. So it means that this matrix wxf, which is you can say connecting the input to the hidden, okay, maybe this one, right? So this matrix is 5 cross 10, okay, because you have 50 connection. And what is x? X is actually a vector of size 10. It is 10 cross 1. Okay, now let's see what is going on in the hidden, you can say hidden state. Okay, so if I have maybe this 5 neurons in the hidden state, then this whole is connected to the next hidden state, which also has 5 neurons, means okay, so these are connected together. So 5 neurons in at time t minus 1 are connected to 5 neurons at time t. This is the same concept we had seen in RNN. Okay, so I expect that you have some memories from that. So what happens here is that this matrix, which is from hidden to hidden, this one, this would be actually 5 cross 5. Why? Because we have 5 here and we'll have 5 in the next time step as well. Okay. And what is the size of ht minus 1? This is also 5 cross 1. And how many bytes we'll have? We have 5 neurons, so we'll have 5 bytes value. So bytes is a vector of 5. So you see, when you do this dot product, a matrix of 5 cross 5 multiplied by 5 cross 1, so you get a 5 cross 1 vector as an output. When you multiply these two, 5 into 10 into 10 cross 1, again you get a matrix of 5 cross 1, and bytes is also 5 cross 1. So eventually you will get a vector of 5. Okay, so you see this ft, maybe I go back to the slide. This would be a vector of size 5 here. Okay, so it means the ft you are computing here, this is a vector of 5. Similarly, this it is a vector of 5. This ot is a vector of 5. So everything which you see flowing on these paths is a vector of 5. Why 5? Because my hidden layer had 5 neurons. If I say my hidden layer has 10 neurons, okay, then all the vectors that are flowing on these black paths, they all would be of length, you can say 10. Okay, so it depends how many you have. Okay, sorry. Now let's go back to the board. Okay, now if I ask you, okay, how many parameters are there in this forget gate? Okay, let me just gain some space. And then we try to compute the number of parameters in this forget gate, and the same will be replicated for every other gate. Okay, so you see parameters. What are parameters? This is a parameter, this matrix, and this. Okay, because X is input, H you are computing, so the parameters are the weights and the biases. So we already said that this WHF is actually a matrix of 5 cross 5. This is a matrix of 5 cross 10. And we have 5 bias values because you have 5 neurons. Okay, so this is like 25 plus 50 plus 5. So this is like 80. So the total number of parameters in the forget gate is 80. And you see, if it is the input, instead of F, I'll be using I here. Okay, this will be I and this will be I. Rest everything remains the same. So it means input gate will also have 80 parameters, right? Similarly, output gate will also have 80 parameters. Okay, so just keep in mind, keep this information in mind. We'll come back to this. Let me go back to the slides. Okay, yeah. Okay, so this is a recap of the discussion we did, that we expanded our, you can say, expression. Okay, so as I told you, this WF, these are actually two matrices. One for the ht minus 1, the other one for the input xt. Similarly, this ht minus 1 xt, we have concatenated both of these. Okay, so this representation actually means this thing. So if we expand this expression, we have a weight matrix multiplied by the previous hidden state, a weight matrix multiplied by the current input, and then we add bias. Since we are assuming 5 neurons in the hidden layer, so the weight matrix from hidden to hidden is 5 cross 5. From input to hidden, because input has 10, hidden has 5, it is 5 cross 10. Okay, so if you just multiply them, eventually you get as an output a vector of size 5 cross 1. So this is what we said, that this ft or all of these are actually vectors of size 5. Okay, whatever is the size of your hidden layer. And this is just, you can say, a visual illustration of this, that once you actually concatenate them, so you have this matrix for the hidden layer, this matrix for the input layer, we simply concatenate them. So actually this part is multiplied by this part, and this part is multiplied by this part, so it stays the same thing. Okay, this we discussed also when we were dealing with RNN. Now coming to the number of parameters, we just computed the number of parameters for the forget gate. Okay, now let's see what is the total number of parameters in this complete cell. Okay, so I go back to all of these expressions. So now you see, this is the forget gate, we just computed 80 parameters. For this input gate, exactly the same thing, so we have 80 parameters. For this, again, exactly the same thing, only the activation function has changed, so again 80 parameters. When you are updating the cell state, there are no parameters involved. Okay, you are reusing F, CT minus 1, IT candidate. So there are no parameters in this expression. Similarly, for output gate, you again have 80 parameters. And similarly, when you are computing HT, you already have, this you already have. So again, there are no parameters for this expression. So it means you can compute the parameters for one of the gates, which is like 80, and then you multiply it by 4, which gives you 320, which is the total number of parameters in this cell. Now you see, you can change anything. You can say, okay, if I have input which is 100 and hidden layer which has 50 neurons, okay, then how do I do that? Let me just do one more example, and then we see the examples which are in the slides. So I say, okay, this is my LSTM cell. The input is of size 100. Okay, and this hidden neuron means there are how many hidden neurons I have here. So maybe they are, say, 32. Okay, so what would be the size of weight matrix which is here? So this would be actually, let's call it maybe WX. This would be actually 32 cross 100. Okay, similarly, these 32 neurons are connected to 32 neurons in the next timestamp. So how many weights? 32 cross 32. And how many bias values? Equal to the number of neurons. Okay, so you see it's the same pattern. This is for one gate. You compute this number and then you can multiply this number by 4. It will give you the total number of parameters. Just to test our understanding, let's compute the number of parameters for a given model. Okay, so just to remind you, embedding layer normally we use with textual data. Okay, this is input, this is output, and embedding layer does not have any bias. Okay, this we remember from our discussion on word embedding. Okay, now suppose someone gives you a model like this in TensorFlow, and they ask you, okay, tell me the total number of parameters in this network. Okay, so when you have to compute parameters of a network, you simply compute them layer by layer and you add them together. Okay, so we start with the embedding layer. So embedding layer, you have 100 neurons in the input, 100, and the next layer has output is 10. Okay, so it's very easy. It is like 10 cross 100 means 1000, and there is no bias in the embedding layer. Okay, so it means first you have maybe like 100 here. Okay, then you have 10 here. Okay, and this 10 is actually going to an LSTM. Now this is your LSTM, and how many hidden you have? 5 here. Okay, so if you compute for this layer, how many parameters are there? 5 cross 10 for the input, plus from hidden to hidden, 5 cross 5. We just did that. How many bytes? 5, because you have 5 neurons in the hidden layer, and then you multiply this number by 4. Okay, so I think you get the same thing, 320. And finally, you have a dense layer. Okay, means after the LSTM layer, means this is your last LSTM layer in which you have 5 neurons, and this is your output layer. Okay, where you also have 5 neurons. Okay, maybe we are solving a 5 class problem. So how many you can say connections do we have here? It's fairly simple. It is like 5 cross 5, because these are 25 connections, and how many bytes? 5. So this actually gives you 30. So you can compute these parameters for each of the layers. Okay, and then you can add them together, and this will give you the total number of parameters. Let me do one more example, and then maybe we can do a pause and we can discuss, right? So now we have 2 LSTM layers, and then we have a dense layer, and for the first layer we already computed. Okay, for the last layer it's very easy, so I have computed for the last layer first. You have 64 and 5, so the number of connections is 64 into 5 and plus 5 bytes for the last layer. So you get for this one you have and this number, which is 3 to 5. Now if we compute for this, we also did compute in the previous slide. This actually came out to be 320. Okay, now let's compute for this one. Okay, so now you see you have an LSTM here which has 5 neurons in the hidden layer, and then you have an LSTM here which has 64 neurons here. Okay, and maybe input is coming from here. This was X, and this is LSTM1, this is LSTM2, and of course you have time on this axis, so it means here also you have 64, here also you have 5. Okay, because you have time on this axis. So now how many for this layer? For this connection vertical, you have 64 cross 5, right? 64 here, 5 here. For this horizontal connection, 64 into 64. right? And how many bytes for this layer? 64 neurons, 64 bytes values. This is for one. You compute this number, but don't forget to multiply it by 4, because you have input gate, output gate, forget gate, and the candidate, right? So you can actually compute this number which is here, and you can just add them. And if you want to convince yourself, or if you want to check your understanding, a very easy way is that when you will run this in Python, model.summary will give you the total number of parameters layer by layer. So you can compute by hand, and you can check your performance by doing model.summary. Now see, this is what we computed, this is what Keras is giving us. 1000, 1000, 320, okay, and then 320. 17920, 17920. For the last layer 325, for the last layer 325. Okay, so this is, if you can compute these numbers, it is actually an indication that you have developed an understanding, right? You see, practically when you are solving a problem, no one would ask you to compute the parameters. You just implement it, you get the output, and that you are done, right? But then why we are stressing on this so much? Because if you can correctly compute all of these numbers, it is a very good indication that you have a very in-depth understanding of how LSTMs work, what are these vectors, what are the sizes, right? So maybe before moving further, we can take a pause here, right? And we can discuss your queries if there are any, right? Let's take a short pause and see if you have any query. Okay, so now again, I'll not be introducing any new concept for the next, you can say 15-20 minutes. We'll be revisiting the same concept but with different examples, right? First, I'll give you a walkthrough, means stepwise animated walkthrough that what is going on in this LSTM cell, and then we'll move to a numerical example, right? I'll give you some numbers and I'll show you the exact computation by solving this like a numerical. Okay, so this also helps you can say develop the understanding of this. Okay? So let's start with the same example of sentiment classification, that there are some online reviews of a product, and we have this training data, and we want to see whether that review is positive or not. So in other words, whether based on that review, we'll buy the product or not, or will recommend this product or not, right? So you see, your review is actually a sequence of words. Okay. So when you read this review, if someone asks you after 2 or 3 days, you will not remember the exact wording of the review, but maybe there are certain keywords which you will remember, like amazing, balanced, and buy again. Okay, so these are some keywords which you will remember, and if someone asks you whether you will recommend this product, so based on these keywords, maybe you will say, okay, yes, you should definitely buy it again, right? So it means you are focusing on certain keywords which are helping you take the decision, and you are ignoring rest of the information, right? So this is basically the same idea, that what is the relevant information your model actually learns. What is the relevant information which is contributing to making a decision, right? So these highlighted maybe set of words, they are suggesting that this is a positive review and we should go for this project, and maybe rest of the words are not that important. They are important from a point of being grammatically correct, but in order to make a decision, they may not be very important, right? If we do it with a simple vanilla RNN, what you do, you will convert all the words into vectors, maybe first into one hot encoding, and then maybe word to vector to convert them into a vector of size 300 or anything. And then one by one, you will feed them to your RNN, and then eventually at the last time step, you will have a fully connected layer, which will give you the rating of the review, right? So at every time step, what we say in RNN, that whatever is your hidden state at time t minus 1, it is fed as you can say input to the next timestamp. So you, when you are looking at the current input, you also look at the hidden state from the previous timestamp. So what happens is that at every time step, you have xt and ht minus 1. You concatenate them, multiply them by a weight matrix, apply the activation function, which is tanh, add bytes, and give the output, which is ht. Okay, so this is repeated as many times as we want. When we move to the LSTM, the idea was more or less same, except that we also had cell state CT, and we have much more of series of operation going on inside the cell rather than simply a tanh layer, right? So what happens here is that first we have input xt and ht minus 1, which we concatenate, and we pass this through a sigmoid. This red one is sigmoid, which actually gives us ft, which is the output of the forget gate, right? So we are concatenating xt and ht minus 1, multiplying by a weight matrix, applying the activation function, adding bytes, okay, and this is what is giving us ft. Similarly, the same thing is fed to a candidate layer and an input gate layer. For the candidate layer, you again apply the weight matrix, add bytes, apply tanh activation function. While for the input, you apply the sigmoid, so you have IT. Okay, so IT is the input and CT is the candidate, which will be added to the cell state. Now, how do you update the cell state? You forget something, you add something. Okay, so whatever is coming from here, it is regulating that what you forget, okay, because you have pointwise multiplication. Then you have something coming from here, IT, and here you have CT. So you take that product, so whatever is going here is what you are adding to the cell state, right? So you see this, I think it should be straightforward. And finally, you have the output gate, okay, which is OT, which is regulating that what you give as output, and by output I mean HT. So HT is actually 10H applied to CT and regulated by the output gate. So you see, initially maybe it looks very difficult, but if you keep looking at it 2 or 3 times, things start to make sense. And whatever I have said, it is a complete summary of all of those steps. Okay, so you see what we did. We combined xt and ht minus 1. Okay, we feed it to the forget layer. Okay, then we feed it to the candidate layer. We also feed it to the input layer. Then we update the cell state, and then we compute the output, which is actually the new hidden state. So if you want to see it in the form of maybe a pseudocode, right? So you have ht minus 1 and xt. We are calling it combine. We are giving it to forget layer, the candidate layer, the input layer. Then we are updating the cell state, which is you are forgetting something and adding something. Then you have this output gate and you are computing ht. Okay. So if you see the literature on LSTM, there are different visual illustrations, right? For example, it is exactly the same thing which we are doing. It is also more or less a similar thing, but the visual representation is different, right? So if you are okay with them, it's fine, right? But I would recommend you that the simplest notation is what we saw earlier, right? So these different illustration can be a bit confusing for you. So I recommend you that you stick to the standard notation, which makes things very easy and intuitive to understand. Okay, if these illustrations make sense to you, I have no problem with that, right? But initially, I recommend you that you should stick to those very basic notation, right? Okay, now before doing the numerical example, I'll just tell you maybe one slide per variant, a few different common variants of LSTMs, right? Of course, I'll not be going into detail, but since you have the general understanding of LSTM, so you can actually guess what is going on. This is a variant which is called LSTM with peephole connection. Now, what is a peephole connection? That you see, whenever we were computing the output of a forget gate, input gate, and output gate, previously we were looking at HT minus 1 and XT. Okay, so this variant says, why not also look at CT? Okay, so you see all of these have this new term, means there would be a new matrix W, which is multiplied by CT minus 1. So it means you are letting your gates look at the cell state. Okay, in a standard LSTM, when you are talking about the gate, you only look at HT minus 1 and XT. So there was a suggestion that why not also look at CT minus 1, which is also a memory of the you can say LSTM, right? So this is one variant, though it is not very common. Then there's another variant which makes sense, that you see previously we were forgetting something and we were adding something new. So this variant says that we should couple forget and input gate, that rather than separately deciding what to forget and what to add, we make this decision together. Okay, so it means we only forget something when we are going to add something. So in other words, once we have ft, so the input gate is actually complement, it is 1 minus ft. Okay, so if you are not forgetting anything, you will not be adding anything new. Okay, so both of these are actually complement of you can say each other. You only forget something when you want to add something new. So rather than having a new IT which has a different weight matrix, now what you are adding is also a function of what you are forgetting. Okay, so this is called a coupled forget and input get. Then another very famous variant which is called gated recurrent unit, GRU, right? It is much simple. Okay, and what it does is that similar to the previous idea, instead of having forget an input gate, it has a gate which is called update gate, right? There's a single update gate. There are no separate gate for getting an input, right? And this has you can say relatively fewer parameters as compared to what you have in a standard LSTM, right? So whenever you are trying to solve a problem or you go through literature, so people will actually first apply a simple RNN, they will apply LSTM, and it is likely that they will apply a GRU. Okay, this is something very common that you will find in different research papers, and then they will do a comparison of these three. And of course, LSTM and GRU, their performance is more or less comparable in many situations, but they easily outperform RNN, right? Because RNN is very, very basic. For simple problems, RNN can work, but for most of the practical problems, you will have to pick LSTM or GRU, and it is hard to say which of these is better. It depends on the problem you are trying to solve, the data you have, and many other parameters, right? Okay, one final comment that will not be going through learning, that how you have learning in an in RNN, but the general idea is the same. Okay, that you learn weight through back propagation. But I have added only one slide just to introduce you with the terminology, that when we are doing back propagation, okay, BP, in a simple network like a CNN or MLP, you already know how to do that. But for an LSTM or for a RNN, we call it BP TT. TT is for back propagation through time, right? Why we are saying it through time? Because when you unfold it, you have different time. You have time on this axis. Okay. So it means you have error on this node, error on this node, error on this node. So your error is back propagating like this. So it is back propagating on the time axis, right? That's why the idea is same. You compute the gradient and you actually multiply it with the learning rate. You add it to the previous, but it is much more complicated because you have error coming from these different timestamp and it is flowing back on the time axis. That's why with LSTM we use this terminology which is called back propagation through time. Okay, so when I will be doing a numerical example, I'll be restricting the discussion only on the forward pass. Okay, and whenever you will have your next assignment, so I have observed that you perform well in a numerical based assignment as compared to in a programming based assignment. So your last assignment of the semester would be forward pass of LSTM, which will be numerical based, right? Because previously your performance in such assignment has been good. So I'll give you more detail once we post it, right? But I'm just telling you that this is what we'll be doing, and we'll be restricting ourselves only to the forward pass, right? So let me take a pause, and then we will continue. Okay, so in this, you can say last part of this particular discussion, whatever we have seen, I'll show you a complete numerical example. And of course, as I told you earlier, we'll be discussing forward pass only, right? And this is what I expect from you. I will not be asking you the backward pass in any assessment, right? So don't worry about it. Okay, so what is our LSTM? We say, okay, we are feeding it a sequence and the length of the sequence is 2, right? Because we have to do it by hand. So definitely we need to have some manageable number, right? So it means this is my input X, which is a vector of 2. Okay, and there are two timestamp x0, x1. Okay, it means I will have I'll feed one and then I'll feed the second one. Okay, so there are two timestamps. In the hidden layer, we have one neuron. Okay, so it means there is one neuron in the hidden layer here, one in the hidden layer. Okay, so now you can guess easily what is the size of this matrix, okay, which is from input to hidden, 1 cross 2 or 2 cross 1, the way you represent. So these are basically the different matrices 2 cross 1 from input to different layers: candidate layer, input layer, forget layer, output layer. Okay. Now hidden layer has one neuron. When you connect them like horizontally, your weight matrix is 1 cross 1. Okay, because there is one neuron. So all the hidden to hidden matrices for candidate, input, forget, and output. This is 1 cross 1. Okay, because I have only one neuron. If I had two neuron here, these would have been 2 cross 2 matrices. Okay. And finally, since I have a single neuron in the hidden layer, so every bias is a single value. Bias for candidate, for input, F for forget, and O for output, right? And why such small numbers? Because we are solving it by hand. Okay. Now let's start working with the forget gate at t equals 0. Okay, because we are feeding the first input, so t is 0. So this is my t is 0. This is my input x naught. And what is ht minus 1? Ht minus 1 is h minus 1, which is coming from here. Since this is the first input, there is nothing coming from here, so we take it 0. Okay, this is what we discussed, that for the first timestamp, you have nothing coming previously. Similarly, you have nothing coming from here because this is the first input. So we also take this equal to 0, a null vector. Okay. Now, the first thing we do is we have to compute ft. This is the expression for ft. For numerical purposes, it's a good idea we expand this. Okay, means we write this term separately, which is weight into input, and this term separately, which is a weight matrix into previous hidden state and bias. Okay, now you have all of these available. T is 0, so you have x naught, which is here. WXF means the weight matrix, which is here. This is also given. And WHF, this is also given. So just plug in the values in this expression. Okay, so you multiply this weight matrix with the input, which is given here, 1, 2. And then you have this WHF multiplied by H minus 1. You add bias, you get a single number. You take the sigmoid of that number, you get pointed. Now, why we are getting a single number? Because the hidden layer has one neuron. Okay, so that's why there is a single number which is flowing on these black paths. If the hidden layer had two neurons, you will have a vector of size 2 like AB, which is flowing on all of these black paths. Okay, so this was for the forget. Now you can repeat this process for you can say all of the other. I'll maybe explain for T0, and for T1 I'll just skip that. So next we have IT and CT. So CT is again you have all of these matrices available. You simply plug in the values, you compute the candidate cell state for T0, and you also compute I0, which is the output of the input gate, right? Which is sigmoid, and here you have tanh. Then you have output gate, again exactly the same thing, but the numbers are different. Okay, so maybe we are getting this as an output. And now finally you can update the cell state, which is you forget something. Okay, so this was the output of the forget gate, but it is since this was 0, nothing is coming from here, so this term will actually be ignored. And then this input gate is controlling what you are adding to the cell state. Okay, so this is your C naught. And finally you compute H naught using the expression. Now the important thing here is, now we are done for t equals 0. Okay, now when you will go to t equal 1, okay, so it means you will have t is 1, so this is H naught, this is C naught, and you will compute these values, okay, which are coming from the previous timestamp. When we were computing previously, we did not have anything coming on this path. But now, when I'll be feeding the second input, I have something coming on this path. What is coming? Which I just computed, H naught and C naught. Okay. So now you see you have a C naught. You have an H naught. So you can repeat this process. Okay. This is trivial, so I'll not be explaining it. Right. You can do this, and you can update the cell state and keep on repeating it as many times as the number of inputs you have. Right. So this brings us to the you can say end of this preliminary introduction to what is an LSTM. LSTM is, you can say, an advanced form of a recurrent neural network. You can say it is a type of a recurrent neural network which is more sophisticated. You have 3 gates: input, output, and forget. You have a cell state, you have a hidden state, and we saw how to compute the number of parameters. It's similar to what you do in an RNN. The only difference is that you multiply it by 4 because you have to do it 4 times, right? And then we saw, I just quickly told you that there's a term which is called back propagation through time, which is used when you are training RNN or LSTM, right? And then at the end, we had seen one complete numerical example, a simple one where the input was only of size 2. There were 2 timestamps and the hidden layer had only 1 neuron, right? But if you can solve it for such a simple example, by hand, you can solve it for any other example, right? So with that, we conclude this topic. If you have anything we can discuss, else we'll move to our next topic.